In this session, we would be discussing about different types of discrete probability distribution. Right, almost 6 to 7 different types of discrete probability distribution is what we are discussing. So, when the word is, we already know the word probability distribution. Right, it's a kind of a function which establishes, which is like f of x, right, wherein you are talking about different values that a random variable could take and their corresponding probability. This is what we are calling as the probability distribution. And if the random variable takes a discrete set of values, countable set of values, we call those kind of distributions as discrete probability distribution. So as a part of the agenda, we would be talking about these distributions specifically under the discrete distribution. So we'll be looking at discrete uniform distribution, then we'll focus on Bernoulli distribution. But yeah, from here you'll find very important distribution. We see a binomial distribution, a negative binomial distribution. So what kind of applications, what kind of data we can use, what kind of distribution is something which is very important for us. Then a special case of negative binomial distribution, which is otherwise called as a geometric distribution, is being looked at. And then we will be moving on to understanding the hypergeometric distribution, and towards the end we would end with the Poisson distribution. So under the discrete distributions category, these are the different kinds of distributions where we would be getting comfortable with, right? So now let's try to go one by one. Initially, let's get started with uniform distribution. This is one kind of a distribution which is there both in the continuous case as well as in the discrete case, the uniform distribution. So this is where we are trying to understand in both the cases. So initially in this session we would talk about the discrete version of uniform distribution, and later on we would be talking about the continuous version of the same. So a random variable x is said to have a discrete uniform distribution in case its probability distribution is given by f of x equal to 1 by k. K is the constant. For x equal to x1, x2, x3, so on, xk. So which in other sense, the probability should be same for all the observations, 1 by k. So if I am talking about throwing a dice, right? So the possibilities are 1, 2, 3, 4, 5, 6. So x equal to 1, x equal to 2, x equal to 3. So this, if I call it as x1, x2, x3, x4, x5, x6. So xk is 6 because there are 6 different possible values that a random variable can take. And if the probability of occurrence of each one of them is simply 1 by 6, then we say that this is following a discrete uniform distribution. So the other way of expressing it is the random variable can take on k different values. Here 6 different values are possible for this random variable. So the random variable can take k different values, each with equal probability, which means the probability of occurrence of one single value for that random variable is 1 by k. So that is the typical discrete uniform distribution, and we just need to know a few important things for this discrete uniform distribution. If x is having the discrete uniform distribution f of x equal to 1 by k, I want to know what is the mean of it. How do I find out the mean? So we are talking about x1, right? x1, x2, x3, so on up to xk. So these are the different possible values that the random variable can take, and we are talking about 1 by k being the probability of occurrence of them. So if I look at the expected value of this random variable, it is nothing but 1 by k into x1 plus 1 by k into x2 so on. So it is nothing but 1 by k into sigma xi, where I is from 1 to k, right? So this is 1 by k into xi, sigma xi is what is becoming the expected value. Now if you look at, in this case, the first term plus the last term, right, these are all uniformly distributed. So this would become, so if you see in this example also, 1 plus 6 is 7, 2 plus 5 is 7, 3 plus 4 is also 7. So I can very well take it as, so you can very well write x1, x2 is nothing but x1 plus some x1 plus d. This you can write it as x1 plus 2d. We are talking about a same gap, x1 plus n minus 1 into d, or k minus 1 into d. So based on this you can very well find out what is the mean. So when you have talked about sigma xi, I can very well write it in this form as well. So overall the mean is coming to be the first term plus 1, or the total number of terms, k terms are there, k plus 1 by 2. Probably here you could see for this example, 1 by 6 into 1 plus 2 by 6 into 1 by 6 into 2. So it becomes 1 by 6 into 1 plus 2 plus so on up to 6, which is 21, which is becoming 21 by 6, or it's becoming 7 by 2. The other way of saying, because there are 6 different variables, 6 different values, 6 plus 1 by 2, making it 7 by 2. So the mean of it is coming out as k plus 1 by 2. Then you can look at the variance of it, right? If the mean is this much, right, the same thing if you go with the example of the dice itself, 1, 2, 3, 4, 5, 6. Then we are talking about the probabilities as 1 by 6. Now, so the mean is coming out as 7 by 2. Now we know variance means I have to find expected value of x squared. So this is nothing but 1, 4, 9, 16, 25, 36. So the expected value of x squared is nothing but 1 by 6 times the square terms, 5 plus 9, 14 plus 16, 30, 55, 91. 91 by 6, or if I want to simplify it, there is nothing much I am able to simplify here. 91 by 6 is coming out to be the expected value of x squared. So overall, now if I want to find out the variance of x, it is nothing but expected value of x squared minus expected value of x whole squared, 49 by 4. Taking the LCMs here, it becomes 182 minus 147, making it 35 by 12, which in other case is nothing but k squared, 6 squared minus 1 by 12. So we can very well say for whatever the different values of k that are possible for x equal to 1 to k. So the same logic, if you generalize it, 1, 2, 3, so on up to k, the probabilities are 1 by k, right? Now what is the mean? 1 by k into 1 plus 2 plus 3, so on k terms. K into k plus 1 by 2. That is the sum of first k terms of an arithmetic progression like this. So which is becoming k plus 1 by 2. So this is the mean part, which is what we are able to show. Variance, I need expected value of k squared. So it becomes 1 squared, 2 squared, 3 squared, k squared. And probabilities are 1 by k across. So overall I can say the expected value is 1 by k times 1 squared plus 2 squared plus 3 squared plus so on k squared. Some of the squares of the first k natural numbers. k into k plus 1 into 2k plus 1 by 6. This is what is the formula for sum of the squares of the first k numbers. So based on that, this is coming out as k plus 1 into 2k plus 1 by 6. Right? So sum of the squares, expected value of x squared is coming out as k plus 1 into 2k plus 1 by 6. Expected value of x is coming out as k plus 1 by 2. From here I can find out the variance of x, which is nothing but expected value of x squared. This is the expected value of x squared minus expected value of x whole squared. So based on this, I can very well find out the LCM being 12. It becomes 2 into k plus 1 into 2k plus 1 minus 3 into k plus 1 whole square. Which, if I take out the commonalities by taking out k plus 1 outside, it becomes 4k plus 2 minus 1k plus 1 is already gone, 3k minus 3. So this is coming out as by 12. So it is also coming out as k plus 1 into 4k minus 3k is k, plus 2 minus 3 is minus 1. K plus 1 into k minus 1 by 12. The other way this gets expanded is k squared minus 1 by 12. So whatever it is, either you can prove with an example, or you can very well take 1, 2, 3, 4 up to k and then get your values as well. Now, if I am going with the MGF, the moment generating function associated, right, the moment generating function associated with the discrete uniform distribution. So expected value of x to the power of r, that is what it is, right? So you can very well bring out, if I am talking about the, expected value of e to the power of tx. Right, this I can very well write it as the expected value of e to the power of tx. That is what is the moment generating function. F of x is already 1 by k. So you can very well take it as 1 by k into e to the power of, so you are adding up because the expected value of e to the power of tx So I can very well write it as e to the power of x values are 1, 2, 3, 4, right? So I can take e to the power of x1, which is 1, plus e to the power 1 into t, e to the power of 2t, plus so on e to the power of 3t, plus so on e to the power of kt. Because x values e to the power of tx. So x is, I'm looking at x being 1, 2, 3, 4. So I'm taking it as e to the power of t, e to the power of 2t, so on. So I can take it as 1 by k. This is a geometric progression, right? So I can very well take sum of n terms of the geometric progression. The first term into 1 minus of r to the power of n. R is e to the power of 2k by 2t by e to the power of t, which is e to the power of t, right? You find 1 minus r to the power of n. To the power of n is k terms. E to the power of n by 1 minus r. So this becomes 1 by k into e to the power of t into 1 minus e to the power of kt divided by 1 minus e to the power of t. So this becomes the moment generating function associated with the discrete uniform distribution. Now you try substituting, you take the differentiation of this with respect to t, right? You take the derivative of this with respect to t and substitute t equal to 0, you should get the mean. So I'll take 1 by k, let me take the derivative of this. 1 minus e to the power of t times the derivative of this e to the power of t into minus kt times, right, minus kt times, well, because I am taking e to the power of t into minus k times e to the power of minus kt. This is the derivative of the first part. Then I have 1 minus e to the power of kt, 1 minus e to the power of kt into e to the power of t. Now divided by 1 minus e to the power of t. So let me take the moment generating function clearly, then we'll do a differentiation. Moment generating function has come out as e to the power of t 1 minus e to the power of kt divided by k into 1 minus e to the power of t. Now let me take the derivative with respect to t. So 1 by k first let me take out as whole constant. So this is the u by v kind of a form. So 1 minus e to the power of t denominator into, I want to take the derivative of the numerator, and that too because it's a product, I'll take it as uv form e power t into minus k e power kt plus 1 minus e power kt into e to the power of t. So this is the numerator part. Then again we have e power t into 1 minus e power kt. The denominator part is minus e power t. This entire thing is divided by 1 minus e power t whole square. The good part looks like 1 minus e power kt into e power t. So I can very well take out 1 minus e power t. This will become, if I expand it, it is becoming 1 minus e power t, 1 by k taking it outside. It is becoming minus k, right? It is becoming minus k times e to the power of k plus 1 into t. 1 minus e power t minus k times e to the power of k plus 1 into t plus 1 minus of e power kt times e power t. So e power t minus e power t, if you are looking at, it is becoming e to the power of 2t, right? It is 1 minus e power plus e power or minus e power 2t times 1 minus e power kt. Now if I am substituting k t equal to 0 altogether, right? So this is coming out as k and this is coming out as 1 minus e power t squared. Now let me substitute t equal to 0. So this is becoming 1 minus of e power 0, 1. So this whole thing is going off. Now what about this? 1 minus of e to the power of kt into e to the power of t. T is 0. So wherever t is coming out to be 0, 1 minus e power kt is becoming 1 and it is becoming 0 altogether. So I am taking a derivative and then substituting t equal to 0. I should get, let me just check something went wrong. The mgf is e to the power of t and 1 minus e to the power of kt divided by k in k, let me take it out altogether, 1 minus e to the power of t. So the derivative of this is becoming 1 minus e to the power of t, and I am multiplying this with e to the power of t into minus k e to the power of kt plus 1 minus e to the power of kt into e to the power of t. So at least this much part is fine. Then e to the power of t into 1 minus e to the power of kt into the derivative of this minus e to the power of t divided by 1 minus e to the power of t whole square. So let me look at this whole thing now. This is 1 minus e to the power of t into all these things, minus e to the power of t into 1 minus e to the power of kt, so on. So this is what is typically working out as the derivative. Now if I am substituting t equal to 0, 1 minus e power 0, which is 0. So this whole part is becoming 0, 0 multiplied by this. Then t is 0, I am taking the derivative. Okay, so because this derivative is in a 0 by 0 kind of a form, when t is 0, the derivative is in a 0 by 0 form. So I have to actually either apply the L'Hospital rule altogether. So that is one more way if I can simplify the whole thing. So only when I am able to do the simplification to that extent, then only I am able to derive mean is k plus 1 by 2. Because here when I am directly substituting t, it is coming into a 0 by 0 form. So I have to extend it to all the values and then take a L'Hospital rule, and then only I can simplify from the moment generating function the value of the mean as well as the variance. So yeah, probably you can very well understand this is the moment generating function. In some cases doing it directly is much more better compared to using a moment generating function to generate your mean and the variance, right? Now the moving to the next type of distribution, which is the Bernoulli distribution. It's a very simple kind of a distribution. If any experiment is performed in such a way that there are only two possible outcomes for this experiment, one is called as success, the other one is called as a failure, and you say the probability of success is some theta, the probability of failure is 1 minus theta. If you are saying the probability of success is 60%, probability of failure is 40%. So that is how you are classifying the probabilities of success and failure. So there are so it could be either a success means there could be a 0 successes, which means it's a failure, or there is 1 success, which is a success. The number of successes, we say that it follows a Bernoulli distribution. So the probability distribution is typically given as theta to the power x, right? If I am talking about the probability of success, so theta is the probability of success, so we are putting it as the theta to the power x. X will be either 0 or 1 depending on whether it's a success or a failure. So if you are saying x equal to 0, then this becomes theta into 1 minus theta to the power 0, 1 minus theta to the power 1. So it becomes 1 minus theta, which is because it's a failure, 0 success. And if I am saying the x equal to 1, theta to the power 1 into 1 minus theta to the power 0, which will become theta, which is nothing but the probability of success. So the number of successes will be either 0 or 1, and the probability distribution is given by theta to the power x into 1 minus theta to the power 1 minus x. This is what is a Bernoulli distribution, but this has paved the way for much more broader version of the distribution, which is called as the binomial distribution, which we are going to take up in the next slide. So moving on to the binomial distribution, is just an extension to the Bernoulli distribution. We said any experiment, there is a success or a failure, right? And theta is the probability of success, 1 minus theta is the probability of failure. Then we are talking about number of successes, which is either 0 or 1. We called it as a Bernoulli. Now this same experiment, if it is repeated n times instead of one time, we are doing a repeated trials, because there are a lot of applications in probability and statistics where we work with repeated trials. Number of trials is more or less fixed. So we know that in each case the probability of success is around theta, which is more or less the same, because the same type of an experiment is performed again and again. So we know that the probability of success is the same theta, and all the trials are independent. So depending on the outcome of the first trial, the second trial's outcomes will not depend. So the second trial's outcomes are completely independent of the outcomes of the first trial, and so on. So all the trials are completely independent. When these kind of situations are there, if I am interested in trying to find out the total number of successes, what is the probability of getting 2 successes, what is the probability of getting 5 successes, 20 successes. So if I am more interested in finding out what is the probability associated with the number of successes, I can very well rely on the binomial distribution. So it says formula for x successes in n trials, the probability of getting x successes and n minus x failures. So the theta is the probability of success. So getting x successes, the probability will be theta to the power x. 1 minus theta is the probability of failure. So getting n minus x such kind of failures is 1 minus theta to the power n minus x. So there is a factor theta for each success, 1 minus theta for each failure. Because all of them are independent, I am trying to find out the joint probability of all of them, which is what is being given as theta to the power x into 1 minus theta to the power n minus x, because this formula is applicable only when all the trials are independent. When all the trials are independent, we said that the probability of the joint probability of their occurrence is same as the product of their independent probabilities, individual probabilities. So the same thing, this can be there in any sequence of n trials, out of which any x of them could be successes, the remaining n minus x of them could be failure. So getting x successes out of n trials could happen in ncx number of ways, because any of them could be a success, any of them could be a failure. Getting n successes, getting x successes in n trials could very well happen in ncx number of trials. So overall the probability of x successes in n trials is nothing but ncx times theta to the power x into 1 minus theta to the power n minus x. So this is what is the probability distribution associated with a binomial distribution. Right? So a random variable x is having a binomial distribution. If you see that the probability distribution for it is given by ncx times theta to the power x times 1 minus theta to the power n minus x. So n trials I have performed, x times I want a success, theta is the probability of success. The probability of getting x successes in n trials, if it is following a binomial distribution, comes with this particular formula. The number of successes in n trials is a random variable. It has a binomial distribution with the parameters n and theta. That is how we define a binomial distribution. So just let's look at a few examples for this. Find the probability of getting 5 heads and 7 tails. So I require 5 heads, 7 tails in 12 flips of a balanced coin. So n equal to 12. So you can treat any one of them as success. So let's say getting a head is a success. So the number of successes is 5, right? Because we are calling head as a success. What is the probability of success, which is theta? The probability of success is 1 by 2. Getting a head, the probability is 1 by 2. So if I have to find out what is the probability of getting 5 heads, we are saying NCX 12C5 into probability of theta to the power x. Theta to the power x is getting 5 successes, and 1 minus theta to the power n minus x, 7. So theta is already half. So you make it as 12C5 half to the power 5, and again 1 minus half is also half to the power 7. So it becomes 12C5 into 1 by 2 to the power 12, whatever it is. This gives me the probability of getting 5 heads and 7 tails in 12 flips of a balanced coin. Let's look at one more example. Find the probability that 7 out of 10 persons will recover from a tropical disease. If we can assume independence, probability is 1 by 0.8 that any one of them will recover from the disease. So theta is 0.8, n is 10, x is 7. So you can very well apply your formula. 10C7, 0.8 to the power x, 7 people recovering, right? 7 out of 10 persons recovering. So it becomes 0.8 to the power 7, 1 minus 0.8, which is 0.2 to the power 3. So 3 of them failing, 7 of them succeeding. So overall will give me the probability of getting 7 successes in 10 different trials that are performed. So tabulated extensively, you will find some tables containing for different values of theta and n, what are the probabilities. Nowadays in almost every kind of computer software, you will find the outputs associated formulas for computing the probabilities from the binomial distributions. So nowadays it's very rare that things are performed in manual calculations. One more important point to understand in this context, when I am looking at a binomial distribution where x successes are looked at in n trials, is also same as getting n minus x successes in n trials where the probability of success is 1 minus theta. Both of them will give me the same number, because you can look at it with respect to failures or successes. Out of n trials, getting x successes with a probability of theta is same as out of n trials getting n minus x successes with a probability of 1 minus theta. Both of them will give me the same result. So in some cases, if I really want to change the process, I can very well change to get my results in a much better manner. Then, if you look at the mean and the variance associated with the binomial distribution, formula wise the mean is n theta and the variance is coming out as n theta into 1 minus theta. So let's look at computing the mean and the variance. Let me take a fresh sheet to try to see if we can compute the mean and the variance. So we got f of x, which is the probability distribution. We got it as ncx theta to the power x 1 minus theta to the power n minus x. So this is the probability distribution, right? Now I want to find the mean. So I'll multiply this with x and I'll sum it across for all the values of n. So if I am simplifying it, right, from 0 to n, all the possible values. So this is coming out as x into n factorial divided by n minus x factorial into x factorial theta to the power x, 1 minus theta to the power n minus x. Now x I am taking out, making it n minus x minus 1 factorial. Right? So this is where again the things are changing. If I am talking about 0, right, 0 into something, anyhow it's 0. So I can very well ignore the 0. I can say I'll take it from 1 to n, and this is becoming n factorial divided by n minus x factorial into x minus 1 factorial, because 1x I am taking out, theta to the power x, 1 minus theta to the power n minus x. Right? Now I can very well make this as, if I take out 1 n out of this I will write it as n into n minus 1 factorial. So that's where I am taking out n. So this is becoming n minus 1 factorial. And here also I will take out a theta. So this becomes theta to the power x minus 1, 1 minus theta to the power n minus x. And this will become n minus x factorial into x minus 1 factorial. You look at this, n factorial. So now n is n minus 1, right? N. So if you look at the total x minus 1 plus n minus x, which is nothing but n minus 1. So total number of trials n minus 1. Out of that I am getting x minus 1 successes, right? N minus 1 factorial divided by n minus 1 minus of x minus 1, which is n minus x factorial into x minus 1 factorial. X minus 1 successes, n minus x failures, right? You are seeing both the things out here. So this summation, which is nothing but sum of the probabilities of all the, so it's a probability distribution, right? We are talking of different random variable values and their corresponding probabilities. So this summation is very much 1. So the overall thing is coming out to n theta. So the mean of the binomial distribution is working out to n theta. Similarly, you can very well compute variance, right? If I have to compute the variance, we know that expected value of the x squared, I can find out expected value of x squared, but in some cases I will write it as expected value of x into x minus 1 plus expected value of x. Look at this, which will be x squared minus x plus x, right? So I can very well find out expected value of x into x minus 1 for this case. Now the same logic I can apply here, right? To find out expected value of x into x minus 1, the same logic I'll do, x into x minus 1 ncx, theta to the power x, 1 minus theta to the power n minus x, sigma. Right? Now if I am substituting x equal to 0 also, it will be the summation will be 0. If I am substituting x equal to 1 also, the summation would be 0. So I can very well change it to 2 to n. Now I also have x into x minus 1, and ncx is nothing but n factorial by n minus x factorial into x factorial. So x into x minus 1 I will take out there also. So this becomes n factorial divided by x into x minus 1 if I am taking out. So this becomes x minus 2 factorial, and this is n minus x factorial. Theta to the power x, 1 minus theta to the power n minus x. Now in this n factorial, let me take out n into n minus 1. Then this will become n minus 2 factorial, right? And this one will be n minus x factorial into x minus 2 factorial. Theta and theta minus 1, I'll take it out. Theta into theta minus 1, theta squared. 2 thetas I am going to take out. which will make it theta to the power x minus 2, 1 minus theta to the power n minus x. So now this whole summation again is becoming equal to 1. So which is making expected value of x into x minus 1 is nothing but n squared minus n into theta squared. This is the expected value of x into x minus 1, n into n minus 1 into theta squared. Now I can very well write variance is nothing but expected value of x into x minus 1, n squared minus n into theta squared, plus expected value of n, which is n theta, which we have already got. So this is becoming n squared theta squared minus n theta squared plus n theta. So this is becoming, if I take out 1 theta out, right, let me take n theta out. So you are getting expected value of x squared is this one, sorry. This is expected value of x squared, which is expected value of x into x minus 1 plus expected value of x, which is giving me expected value of x squared, minus I want expected value of x whole squared, which is n square theta square, to get my variance. So that's where these two are going off. This becomes n theta into 1 minus theta. So that is how I am able to compute the variance associated with the binomial distribution. It is becoming n theta into 1 minus theta. Right? So that's one more way we can find out the mean and the variance associated with the binomial distribution. Now, the next thing that I can look at in the same context is the moment generating function associated with the binomial distribution, which is coming out as 1 plus theta times e power t minus 1 to the power n. This is the moment generating function. You can very well try out using expected value of e power tx for each of the steps. You can just play around and try to find it out, but otherwise you can readily use the formula mx of t is 1 plus theta times e power t minus 1 to the power n. Now if you want to find out the mean and the variance from this moment generating function, I can take the first derivative of this, right? The first derivative of this, if I do it with respect to t, the first derivative of this is becoming, so this is this whole thing, if I am assuming it as x, so this is becoming n into x to the power n minus 1. So 1 plus theta e to the power of t minus 1 to the power n minus 1, and I take the derivative of the internal part. The derivative of the internal part is theta e power t. Right? The derivative of the internal part is becoming theta e power t. So it is becoming n theta e power t into 1 plus theta e power t minus 1 to the power n minus 1. And if I substitute theta equal t equal to 0, so t equal to 0, e power 0 is 1, 1 into n theta is n theta, 1 plus e power t is 1, 1 minus 1 0, so this whole thing is becoming 0 into 1, which is making it n theta. So I can get the mean as n theta out here. Now the same logic, if I am applying it to get my second moment, so the first moment is coming out as n into 1 plus theta times e power t minus 1 into theta e power t. Now I'll take the derivative once again by taking out n theta outside. 1 plus theta e power t minus 1 multiplied by e power t plus e power t into if I take the derivative of this is theta e power t. So this is the second derivative that is coming out, right? Oh, sorry, this is to the power n minus 1 is also there. So let me do it again. N into n theta e power t into 1 plus theta e power t minus 1 to the power n minus 1. So I can very well take out n theta. Now find out the derivative e power t n minus 1 into 1 plus theta e power t minus 1 to the power n minus 2, right, into theta e power t. So this is one part plus 1 plus theta e power t minus 1 to the power n minus 1 into e power t. This is the second part. So I'll take out n theta. Now let me start substituting theta equal to 1 to simplify this whole thing. Theta equal to 0. E power theta is 1. Then it is n minus 1 into t. If I am substituting 0, 1, 0, e power 0 is 1. So this part is 0. 0 into something is 0. The whole thing is 1. 1 minus 1 to the power n minus 2, which is also 1. So this whole thing is n minus 1 into e theta, n minus 1 into theta, e power 0 is again 1. So this whole term is becoming n minus 1 into theta plus, here if I substitute e power t, if I am putting it as 0, 1 minus 1 0, theta into 0 is 0, 1 plus 0 is 1. So this whole thing is becoming 1 into e power t is 1. E power t is 1. So this whole thing is coming out to n theta into n minus 1 theta plus 1. That is what is coming out as expected value of x squared. So which is otherwise coming out as n into n minus 1 theta squared plus n theta. So n squared theta squared minus n theta squared plus n theta is coming out as expected value of x squared minus expected value of x whole squared. So if I am taking these two things out, that is what will give me the variance, which will work out as n theta into 1 minus theta. So I can very well use the moment generating function, take the derivatives to get my first moment, second moment. From there I can very well use the relation expected value of x squared minus expected value of x whole squared is nothing but the variance of x. So I can use all these kinds of mechanisms. For every distribution, I am looking at the mean, I am looking at the variance. Even for the above numericals, I can very well find out the mean and the variances here. Right? N is 10 and theta is 0.8. So n theta, which is the mean, is coming out as 8. And if I am talking about variance, n theta into 1 minus theta, 10 into theta into 1 minus theta, 8 into 0.2 will be 1.6. So the variance for this kind of an example is 1.6 and the mean is around 8. So we can very well use this to solve the numericals associated with the binomially distributed data set. Right? Now, from the binomial distribution, now let's move on to the next one, which is the negative binomial distribution. Here, the slight difference is, I am interested, instead of saying out of n trials, I want x successes. Now we are talking about the kth success, right? In which trial I am getting the kth success. the number of trial in which I am getting my kth success. So if I am talking about the third person to catch a disease is the 10th child who is exposed to the disease. Or if I am talking about a burglar who is caught for the second time in his 8th job that he has typically performed, stealing job that he has performed. So this is where the binomial distribution comes into picture. I am looking at in which trial did the kth success typically come out. What is the probability associated with the number of trials in which the kth success is going to come up? Now within this, if I am always talking about the first success only, right, here in general we are calling it as kth success. In which trial, what is the trial in which the kth success has typically occurred? That is what we are calling as the negative binomial distribution. But within that, if I am focusing on getting the first success, this is a special case of negative binomial distribution, otherwise called as a geometric distribution, which I will be discussing in the next slide. But geometric distribution is a special case of negative binomial. In negative binomial, I am looking at in general the kth success is coming in which trial? Is it the first trial, second trial, 10th trial, 20th trial? Which one is it? I am trying to find out the number of trials in which the kth success has occurred. Whereas if I am looking at number of trials in which the first success has occurred, we are calling it as a special case of negative binomial distribution, which we are calling as a geometric distribution. So in general, the definition of the negative binomial is I am looking at the kth success on the xth trial. Obviously, k minus 1 successes should have come by x minus 1 trials. So this is where we will use a binomial distribution. I have done x minus 1 trials and I have already got k minus 1 successes, which would have occurred like x minus 1 c k minus 1, because out of x minus 1 trials I need k minus 1 successes. Theta is the probability of success, so it becomes theta to the power k minus 1. 1 minus theta is the probability of failure, it becomes x minus 1 minus k minus 1, which becomes x minus k. So this is the probability of getting k minus 1 successes in x minus 1 trial. And obviously the xth one, the next one is going to be a success. So the probability of that success is theta. Now this is what we call as the negative binomial distribution. B star is the representation. So wherein, because another theta I have multiplied, it becomes power k, x minus 1 c k minus 1, theta to the power k, 1 minus theta to the power x minus k. That is what we call as the probability distribution associated with the negative binomial distribution. The number of trials in which the kth success occurs is a random variable having a negative binomial distribution with parameters k and theta. K talks about the kth success and theta is talking about the probability of success. In some cases, we also call it as a binomial waiting time distribution, or in some textbooks, it's also called as a Pascal distribution, which is otherwise very commonly called as a negative binomial distribution. So as an example, let's quickly look at this. If the probability is 0.4 that the child exposed to a certain contagious disease will catch it. So theta is coming out as 0.4. What is the probability that the 10th child exposed to the disease, so x we are talking of is 10, will be the third to catch it. So the k we are talking about as 3. So based on this, I can very well simplify the problem. X minus 1 c k minus 1, which is 9 c2, right? X minus 1 c k minus 1, theta to the power k, 1 minus theta to the power x minus k. So this is what is the computation. So based on this, you can simplify it. to get what is the probability that the 10th child exposed to the disease will be the third to catch this disease. Now, regarding the same, there are a few more interesting points to keep in mind regarding the negative binomial distribution, where we are bringing in the relationship between the binomial and the negative binomial distribution. If you see here, in a binomial distribution, if we are talking about kth success, k successes in x trials, right? X trials, k successes, theta being the probability of success. Here we are talking about the kth success coming in xth trial. So these two are linked by k by x times the binomial distribution. So the negative binomial distribution values will be equal to k by x times the binomial distribution values itself. Now if you look at the earlier example, the previous one, where our x was 10, k was 3, theta was 0.4. If I go with the binomial distribution way, right, if I am going with the binomial distribution way, I would have computed as 10C3 probability of success to the power 3, probability of failure to the power n minus 3, which is 7. So this is the binomial distribution associated values. Whereas when we looked at the negative binomial distribution, we got the answer as 9C2 into 0.4 to the power 3, and we have also got it as 0.6 to the power 7. Now if you look at the difference between the two, so 10C3, so these two parts you can leave them as it is. Now you look at the 10C3, 10C3 is nothing but 10 factorial divided by 7 factorial into 3 factorial. The otherwise you can write it as 10 into 9 factorial divided by 7 factorial, right, 3 into 2 factorial. So it is becoming 10 by 3 into 9 factorial by 7 factorial into 2 factorial. All this is becoming 9C2. So I have simply made it as 10 by 3 times this. So my k is, so here it is working out to this multiplied by 10 by 3 is giving me the value that is associated with the negative binomial distribution. Right, 10 by 3 times whatever you have multiplied with the negative binomial, we are getting the binomial. Or you take the reverse, 3 by 10 times whatever you are multiplying the binomial, you should get the value corresponding to the negative binomial distribution. So that's one more important relationship associated with the negative binomial distribution. Then coming to the mean, in case of negative binomial distribution, you can find the mean is k by theta. So for our example, 3 by 0.4 is the mean, and the variance comes out as k by theta times 1 by theta minus 1. 1 by 0.4 is 2.5 minus 1, which is 1.5. So the mean is going to be 3 by 0.4, which is 7.5. The variance is going to be 3 by 0.4 into 1.5. 7.5 into 1.5, making it 10.25. That's how we are solving the negative binomial distribution, the values in terms of computing the mean and variance for those particular values. Now, as I have already simplified, geometric distribution is a special case of negative binomial distribution where you are taking k equal to 1, because I am only interested not in the kth success but only in the first success. So whatever we have taken in case of negative binomial, wherein we have taken x minus 1 c k minus 1 theta to the power k 1 minus theta to the power n minus k. Substitute k equal to, sorry, x minus k. substitute k equal to 1. So this becomes x minus 1 c 0, which is always 1. Theta to the power 0, k is 1. So theta to the power 1 is theta. 1 minus theta to the power x minus 1. So this is what is the geometric distribution. It's a negative binomial distribution with k equal to 1. Right? So if I take this as an example, if the probability is 0.75 that an applicant for a driver's license will pass the test on any given try, what is the probability that the applicant will finally pass the test on fourth try? So I am getting my x as 4. So my answer would come out as theta into 1 minus theta to the power x minus 1, which is 3. I can very well compute the same. So this is 3 by 4 and this is 1 by 4 cube, which becomes 1 by 64, overall becoming 3 by 256. You can very well simplify it to get the probability value. Alright. Now, moving on to the next one, which is the hypergeometric distribution. It is more or less similar to a binomial distribution, but with one major difference. In binomial distribution, we have made that the trials are very much independent. Whereas in case of hypergeometric, the trials are not independent. There is a sampling without replacement. Right? I am looking at the sampling not with. So binomial distribution will have sampling with replacement, whereas in hypergeometric, I am looking at sampling without replacement. So if I am talking about n elements overall, out of which m of them are successes. So we are talking of n trials, m of them are successes and n minus m are failures. So the probability of success here is m by n. So out of which, this is the overall population space. N elements are there, m of them are successes and the remaining are what are treated as failures. Then the probability that I will get x successes in n tries. So which means I am getting x successes in n trials. So overall, out of the capital N elements that are there, I am picking some small n elements which can be picked in NCN ways. And now regarding the success, there are total m successes, out of which I am getting x successes in my trial, and out of the remaining n minus m which are failures, I am getting n minus x failures out of them. So this is why we are getting the probability of getting x successes in n trials follows a hypergeometric distribution with parameters n, capital N and m. M is the overall number of successes, n is the overall number of trials, overall number of elements, the population space, and small n talks about the number of trials in which we are talking about. The successes or failures. Look at this example, that would be much comfortable for you. As a part of the air pollution survey, the inspector decides to examine the exhaust of 6 of the company's 24 trucks. So overall, there are 24 trucks, right, which is capital N. But as a sample, the inspector wanted to look only at 6 of them, which is the small n is equal to 6. If out of the if 4 of the company's trucks emit excessive amounts of pollutant, so out of this, out of 24, 4 of them are treated as success, means they emit pollution. What is the probability that none of them will be included in the inspector's sample? So I want probability of x equal to 0. So I can directly compute using my formula mcx. So out of the 4, I am not picking any, 4c0. Out of the remaining 6 So out of the remaining 24 minus 4, 20. Out of the remaining 20, I am picking all the 6. Out of the remaining 20, I am picking all the 6. Divided by out of 24, I can pick some 6. So this is the probability that none of them will be included. None of those 4 trucks which are emitting high amounts of pollution, they are not included as a part of the selection. So this kind of examples form the hypergeometric distribution. And now to put up a few things, the mean of the hypergeometric distribution comes out as small n into capital M by n. Variance comes out as nm into n minus m into n minus n divided by n squared into n minus 1. So if we want to quickly look at the proof associated with it, or the derivation associated with this, right, we have already given the probability density function is mcx and n minus m c n minus x divided by ncn. This I am multiplying it with x, and I am substituting. If I want to find out the mean, I am substituting it, I am summing it from 0 to n for the values of x. Okay, now let me simplify this. This becomes m factorial divided by m minus x factorial into x factorial x into, this becomes n minus m factorial divided by, or I can keep it as it is, n minus m c n minus x divided by ncn. Now this I will take it out, making it x minus 1 factorial. So because I am making it x minus 1 factorial, right, I will simply take it out. I'll take one m out of this. So this m I am taking out, making it m minus 1 factorial divided by m minus 1 factorial divided by m minus x factorial into x minus 1 factorial, and this is, I'm keeping it n minus m factorial, n minus m c n minus x divided by ncn. And if I also take this one out, ncn also if I take here, this is what is becoming m factorial divided by m minus x factorial into x minus 1 factorial. So this becomes m minus 1, so summation is still there, m minus 1 c x minus 1, and this is becoming n minus m c n minus x. Now if you are saying x minus 1 is some y, and if you are putting n minus 1, if I take it as some m, right, n minus 1 I'll take it as m, x minus 1 I'll take it as some y. So the mean is typically coming out as m by ncn, and this is coming out as m minus 1 cy, and it is coming out as n minus m c m minus y, because this is coming out as n is coming out as m plus 1, right. I am getting m minus 1 cy, and I will write it as n minus m c m minus y. So based on that, so I am getting here MCR. Probably if you are looking at this, if you are using the summation MCR into NCK minus R, you can very well write it as M plus NCK, right? So that's the same thing. If you are summing it across, I can very well use this relationship MCR into NCK minus R. I can very well use M plus NCK. So the same logic, if I am using, I can very well write it as M. So these two things, when I am integrating, it is coming out as M divided by NCN n minus 1 Cm. So based on this, I can very well simplify it to get Nm divided by N. So either I can solve it step by step, or I can very well remember my formulas associated with the mean and the variance associated with the hypergeometric distribution, which is simplified to the above case. And the moment generating function in case of hypergeometric distribution is much more complicated, right? So in many cases we may see that the hypergeometric distribution can be very much approximated through a binomial distribution as well, especially when n is very large, right? The total number of observations is very large, but you are sampling a very small set out of it. Like in the earlier case, 24 is the capital N, 24 trucks are there, but you wanted to examine only 6 trucks, which is N is very small compared to N. Then the binomial distribution with parameters N, which is 6, and theta, which comes out as m by n, 6 by 24, is used to approximate the hypergeometric probability. If I look at the same example which we had earlier, in the earlier case, we got the result as 4C0 into 20C6 divided by 24C6 if I am going with a hypergeometric. But in case of binomial, if I am going with, right, out of 6 getting 0 successes, so 6 is 0, theta, which is 1 by 4 to the power 0 into 3 by 4 to the power 6. So this is the binomial approximation to the hypergeometric for the same example, whereas this is the hypergeometric related probability. So if n is very large, small n is very small, these two probabilities should be more or less one and the same. Now another example on the same lines. Among the 120 applicants per a job, only 80 are qualified. So if 5 of the applicants, which is very small, are randomly selected for the in-depth interviews, find the probability that only 2 of the 5 qualified for the job by using the formula for hypergeometric distribution. The formula for hypergeometric is MCX 80C2 remaining 40C 80C2 into 40C n minus x, which is 3, divided by 120C5. This is the hypergeometric way of finding the probability. Whereas if I am going to binomial distribution way, now I will get capital N is large, small n is small. So n is 5, theta I can very well take as m by n, which is 80 by 120, which I can take it as 2 by 3. NC2, 5C2 into theta to the power 2 into 1 minus theta to the power 3. So this works out as 10 into 2 square, 4 by 9 into 1 by 27. So 40 by 243 is the probability here, and whereas here I need to find out the probability. Both of them should be approximately equal, because in this case n is very large, capital N is 120, small n is only 5. So I can very well go with an approximation of the binomial distribution to solve problems of this kind. Alright. Then once we are done with the hypergeometric distribution, now we are also looking at another distribution, which is the Poisson distribution. So in this case we are looking at n is very large, small n. Right? When n is very large, if I have to compute the binomial probabilities where you are using NCX, if n is very large, it's very difficult to simplify the binomial probabilities. Right? Simple calculations will not do the job. Now this is one specific scenario where the Poisson distribution is helping us in terms of approximating the binomial probabilities, especially when n is going very close to infinite. The probability of success is very small, very close to 0, but n theta, which is the multiplication of the number of trials and the probability of success, that is very constant to a large extent, which we generally represent as lambda. This is the scenario where we can approximate the binomial distribution to a Poisson distribution. So the limiting distribution of a binomial distribution becomes a Poisson distribution, which will have the distribution function as lambda to the power x e to the power of minus lambda by x factorial, where lambda is working out as n theta, which is more or less a constant from the binomial distribution example, right? So we could very well try looking at how this formula has cropped up, right? So we have already said lambda is n theta, right? So based on this, if I have to use my binomial distribution, theta is nothing but it is lambda by n. So let me use my binomial distribution formula. The probability distribution for binomial distribution, NCX theta power x 1 minus theta to the power n minus x. So wherever theta is there, I'll put lambda by n. So this becomes NCX lambda by n to the power x 1 minus lambda by n to the power n minus x. Now this I can very well write it, this one NCX I will write it as n into n minus 1 into n minus 2, so on. I'll write it as n minus x plus 1, right? Because NCX, n factorial divided by n minus x factorial into x factorial. So I will write this as n into n minus 1 into n minus 2, so on, n minus x plus 1. Right? So this n minus x factorial, I'm cancelling it out here, whereas the remaining thing is n minus x plus 1. I'll take it as x factorial. So this I'll take it as lambda by n to the power x 1 minus lambda by n to the power n minus x. So now, and the next thing that I want to take is dividing one of the factors n in lambda by x to the power n, right? Lambda by n to the power x into each factor of the product. So I have completely broken this out into each of the factors of the product. Now what I will typically take is 1 minus lambda by n to the power n minus x. I will write it as 1 minus lambda by n to the power minus n by lambda, right? I'll write it like this. to the power, so 1 minus, so it's like 1 minus lambda by n to the power n into 1 minus lambda by n to the power minus x. So, so I'm breaking this, right? I'm writing it as 1 minus lambda by n to the power n into 1 minus lambda by n to the power minus x, which will make it 1 minus lambda by n to the power n minus x. Now this part 1 minus lambda by n to the power n, I will write it as 1 minus lambda by n to the power minus n by lambda and to the power minus lambda, so that this is nothing but n, and this part is 1 minus lambda by n to the power minus x. And coming to this part, I am dividing this by, now if you see here, I am dividing it by n, all of them. So because here you have lambda power x by n power x. So I am dividing the entire thing by n power x, which is nothing but n, all of the things are there. So which will become 1, because I am dividing it by n kind of x times I have this particular n. So I am dividing all of them. So which is becoming 1 into 1 minus 1 by n into 1 minus 2 by n into 1 minus of x minus 1 by n. So I am dividing all of them by n power x. So this becomes divided by x factorial. Now this part is only lambda to the power x, and this part is the same. This part is also the same. Now we will substitute n equal to infinite, because we are saying n is large. So this becomes 1 minus 1 by infinity is 0. So this is 0, this is 0. All these terms are becoming 0. So the whole thing here, the numerator is becoming simply 1. The numerator, this whole thing in the numerator is becoming 1. 1 minus x by lambda, 1 minus lambda by n to the power minus x also, this also is becoming 1. Then this one, 1 minus lambda by n to the power minus n by lambda, which is nothing but 1 minus lambda n to the power n minus n by lambda, this is nothing but e. So the whole thing is becoming by x factorial. So this is 1 by x factorial lambda power x. This is becoming e to the power of minus lambda. So the whole derivation is coming out e to the power of minus lambda power x by x factorial when n is becoming more and more closer to infinity. This is the kind of a derivation that we can very well go with when we are dealing with an approximation to a binomial distribution as a Poisson distribution. So the number of successes is a random variable having a Poisson distribution with a parameter lambda. So what we typically see is Poisson distribution ends up as a very good approximation to the binomial distribution when n is greater than or equal to 20 and theta is less than or equal to 5, which means n theta in this case is coming out to 0.1. Very small values of n theta are coming out, but they are more or less constant. In that case, I can very well use the Poisson distribution as a much better approximation to the binomial distribution as such. Let's take a couple of examples to simplify the stuff. If 2% of the books bound at a certain bindery have defective bindings, right? 2% of them are defective. Use the Poisson approximation to the binomial distribution to determine that the probability that 5 out of 400 books bound by this boundary will have defective pieces. So we want to know 5 out of 400, so x is 5. Now lambda we are getting as only 2% of the books. So 400 into 0.2. That is what is coming out as lambda, which is working out as 8. So I am very much interested in finding out the probability that x equal to 5. E power minus lambda, lambda power x by x factorial. This is what will be the probability that 5 out of the 400 books which are bound at this particular bindery will have defective bindings. Similarly, records show that the probability is 0.00005, very small probability, that the car will have a flat tire while crossing a certain bridge. Use the Poisson distribution to approximate the binomial probabilities that among 10,000 cars, so lambda is n theta, which is 10,000 divided by 0.00005, which will be 0.5, right, which would be 0.5, because this into 0.5 is 5,000, 0.05 is 500, so this will work out to 0.5. So 0.5 will be the flat tire, so lambda is 0.5. To approximate the binomial probability that among 10,000 cars, exactly 2 of them will have a flat tire, x equal to 2. So it becomes e power minus lambda, lambda power x divided by x factorial. So this is what is coming out as exactly 2 flat tires, which is which we could very well find out the result. Lambda is 0.5, x equal to 2. We can very well simplify the numerical quite comfortably. So now we have solved the probabilities associated with the Poisson distribution. Then we are also looking at the mean and the variance. This is one distribution which has the same value for the mean as well as variance. Both of them are lambda. The mean and the variance, both of them work out to be lambda. The moment generating function comes out to e to the power of lambda into e power t minus 1. Because we know that if you look at e to the power of tx times, right, if I'm talking about moment generating function, it is e to the power of tx and multiplied by the f of x, which is e power minus lambda, lambda power x divided by x factorial. So in this case, I can very well go with, I'll take out e power minus t. If I'm e power minus lambda, if I'm taking out, it is nothing but I can very well write it as lambda e power t times x divided by x factorial, right? I can very well write it, and which is extended between 0 to infinity. X is going between 0 to infinity. So I can take e power minus lambda into lambda e power t to the power x by x factorial. I can very well take this as a Maclaurin series of e to the power of z kind of stuff, because e to the power of z will work out as 1 plus z square by 2 factorial plus so on. So this is very much, if you are looking at lambda e power t, I can very well look at it as e to the power of, so this whole thing, if I am taking it as e to the power, so the z is coming out as, if I can very well take in this case z as lambda e to the power of t. So that way I can very well take this as z is, I'll take it as lambda e power t. So this is becoming e power minus lambda into e power lambda e power t, which is otherwise becoming if I take out the lambda out, right? Because otherwise it becomes e power minus lambda plus lambda e power t, or I will write it as e power lambda into e power t minus 1. So that is what will become the moment generating function associated with the Poisson distribution. Now, if I want to find the mean from it, I take the derivative of this, right? So e power lambda e power t minus 1 multiplied by the derivative of this lambda into e power t derivative is e power t. This is the first derivative. So put t equal to 0. This is becoming 1 minus 1 0. E power 0 is 1. 1 into lambda into 1, which is lambda. The first derivative is becoming lambda. Now let me take the second derivative. Take out the lambda out altogether. This multiplied by this. So this becomes e power lambda e power t minus 1 into e power t plus e power t into e power, so this is becoming e power lambda e power t minus 1 into lambda e power t. Right? That is what is the derivative of this. So becoming lambda into, when I start putting t equal to 1, t equal to 0, sorry, when I am substituting t equal to 0, e power 0 is 1 minus 1 0 multiplied by lambda is 0, e power 0 is 1. 1 into e power 0, 1. So this whole thing is becoming 1 plus, then e power 0 is 1, 1 minus 1 is 0, e power 0 is also 1, lambda e power 0, so this is lambda. So which is working out as lambda plus lambda square, that is expected value of x square. Now if I want to find out the variance, it is nothing but expected value of x squared minus expected value of x whole square, which is again working out to be lambda itself. So even from moment generating function, I can very well find out the values of expected value of x as well as expected value of x square and even the variance of x, right? Now, though we have seen Poisson distribution is a limiting version of the binomial distribution, there are so many real world applications that do not have any kind of a direct connection with the binomial distribution. Especially, there are lots of applications associated with the Poisson distribution where I am trying to compute the number of successes in a given time period or in a given specific region. Number of successes in a given time period or in a specific region where the number of successes occurring in non-overlapping time intervals is independent. So when I am talking about 1 hour, number of successes in first quarter, first 15 minutes versus number of successes in the next 15 minutes, number of successes in next 15 minutes and the last 15 minutes, they are all independent. Or when I am talking about the region, this is the area of that region. Number of successes in this part is independent of number of successes in this part. So every region, the number of successes are completely independent. Probability of a single success, right? One success occurring during this period is very, very minute. Or within this region, probability of one success that is occurring is in a very, very small region or very short time interval. It should be proportional to the length of the time interval. So depending on the length of the time interval, so if I am talking about this is a 15 minutes time interval, then I am looking, if I look at it as a 1 hour time interval, then the probability of the success should be proportional to the length of the time interval itself. If the probability of success here is t, the probability of success over 1 hour should be around 40. Probability of success in 15 minutes is t, then the probability of success over the 1 hour interval should be around 40. So that is what it means. Probability of single success occurring in a very short time interval or in a very small region should be proportional to the length of the time interval or the size of the region. And probability of more than one success occurring in this short time interval is almost negligible, that I can omit it. In that case, there are lots of applications of the Poisson distribution that do come up. So let's take a couple of examples to understand that. The average number of trucks arriving on any one day, this is the time interval, at a truck depot in a certain city is known to be 12. Average number means lambda equal to 12. What is the probability that on a given day fewer than 9 trucks, right? Probability of x less than or equal to 9. Fewer than, so I don't need equal to, it is x less than 9 will arrive at this depot. I can very well use the Poisson distribution. E power minus lambda lambda to the power x. So here my x should be 0, 1, 2, so on up to 8. Any of these values. So e power minus lambda per 0 by 0 factorial plus e power minus lambda power 1 by 1 factorial, so on e power minus lambda power 8 by 8 factorial. So this is what is going to give me what is the probability that on a given day fewer than 9 trucks will arrive at the depot. Now look at one more. If successes occur at a mean rate of lambda per unit time, okay, per small unit of time, the success is occurring at the rate of lambda or even in a small region, then the number of successes in an interval of t units, when this is 1 unit, the success is occurring at the rate of lambda per unit. So I have so many units like this. It becomes lambda t, which would be within t interval or in t specific regions. I can very well say that the mean success rate would be lambda equal to alpha t. So even for the probability computation, I can very well take the new lambda as alpha t and I can go ahead in terms of solving the numericals as well. This is where you can take the example. A certain kind of sheet metal on an average 5 defects per 10 square feet, right? So alpha is 5 per 10 SFT. If we assume a Poisson distribution, what is the probability that a 15 square foot sheet of the metal will have at least 6 defects? So the lambda is 5 into, I'm talking about 15 square foot. Per 10 square foot it is 5. So for 15 it is 15 by 10, which is working out to 7.5. My lambda is 7.5 and I want to say we'll have at least 6 defects. So greater than or equal to 6. So which is always like 1 minus of probability of x less than 6. So I'll find it out as 1 minus of probability of x equal to 0 plus x equal to 1 plus and so on probability of x equal to 5. And in all these cases it becomes e power minus lambda power x divided by x factorial. E power minus lambda power x divided by x factorial. Up to 5 I'll do it and finally simplify the numerical. So these are different ways, these are the different kinds of numericals that I can solve with respect to Poisson distribution, right? This is what I wanted to talk of with respect to discrete distributions. We have talked enough regarding the discrete uniform distribution, talked about Bernoulli distribution, binomial, negative binomial, geometric, hypergeometric, and finally we ended up with the Poisson distribution. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.